our plenary speaker will be joining us very, very shortly. And I am Arokia Nathan from Cambridge Touch Technologies, and I was supposed to be chairing yesterday's session, but I had other commitments as well right at the same time, and so I made a swap with Dr. Luigi, who was supposed to be the original chair.
Hello, everyone. I'm very sorry about that.
No problem, Richard. No problem. We're just settling down as we speak, and I was just mentioning something about, I wasn't supposed to chair your session, but something came up yesterday, so
no problem.
I swapped with Luigi. So tell me when you're ready, and I can then do a formal introduction.
Okay, perhaps just 1 minute so I have the screens ready, and then I will be all prepared.
Okay. This is just a casual chat on the side while you are getting ready. It seems that these virtual events are turning out to be quite a success. The large number of registrations and, the fact that they can actually, once it's on video, they can look at your talk at any time as well. So that's a lot, very, very flexible, very much incongruent with the theme of the meeting on flexible.
Yeah. So I'm ready. I guess once you've introduced me, I'll share my screen.
Yes, that'll be great. Okay, so this is welcome to the final day of the conference. Hope you have had a very enjoyable time. There were very, very interesting talks through the previous 3 days so far. It's a pleasure to announce today's plenary speaker, Dr. Richard Price, who will tell us all about how to create more innovations in this new emerging area of flexible electronics. Just a few words on Dr. Price. He has over 20 years of experience in the development and commercialization of a wide range of new technologies based on novel processes, materials, and in particular, flexible electronics. Richard has a BSc and a PhD in chemistry from the University of Durham, and he has led PragmatIC, that's a difficult one, PragmatIC technical teams to develop FlexLogIC and FlexIC products, and is an inventor, co-inventor of more than 25 patent families. It's a pleasure to have you here, Richard. Please go ahead, and we look forward to your presentation.
Thank you, Arokia. And hopefully you can now see my my presentation that I'm sharing.
Yeah, very nice and clear.
Okay, and sorry for keeping everyone waiting. I prepared very carefully for this conference. Originally it was in Manchester, which is my hometown, but I made sure that my children were not on Netflix or anything else. And then unfortunately a Windows update decided to intervene. So apologies for keeping you waiting, but it's a pleasure to be here today and to be part of a fantastic conference from the past few days. So as Arokia mentioned, I'm going to talk about PragmatIC, our flexible electronics technology, and some of the innovations that we have been developing and we hope to develop with that. So just starting with an introduction to PragmatIC. So we're now nearly 10 years old as a business, and originally we were based in Cambridge within the university, and more recently within the science park. But for the past 7.5 years, we've also had a base in Sedgefield in the northeast of England. And we have around about 90 staff now across those two sites, and we cover quite a broad range of different areas really of the electronics value chain. So we've built up a team of expertise from industry, from semiconductors, electronics and manufacturing, but also from world-leading universities and institutes like TNO, Cambridge, and so forth. Within Cambridge, we have our corporate headquarters, our business development, applications, test development, and design activities. And in Sedfield, we have our operations, our first production line, and associated with that are process engineering and R&D activities. We're very fortunate to have some fantastic strategic shareholders in the business. These include ARM, which is the world's #1 semiconductor IP company, and they now have deployed more than 150 billion ARM cores to power many of the mobile devices across the world. Avery Dennison, which is a Fortune 500 company with more than $7 billion turnover. And not only are they leaders in labeling and packaging materials, but they're also the world's #1 RFID inlay manufacturer. And last but certainly not least, Cambridge Innovation Capital, or CIC, who are a very experienced technology investor. They build businesses for the long term, and they really focus on companies that have brilliant technologies that they can back. So all of this has allowed us to build our first production line and to move that into delivering our first products, which I'll talk about. So as we've heard at the conference, flexible electronics now is real. There's been more than 30 years of activity here, but we have now bendable displays. We have flexible and stretchable devices that are wearable on the body. We have power and flexible batteries and photovoltaics. And we have printed circuitry, which can be built into things like RFID tags, but also a whole host of other types of products as well. But what about integrated circuits? So how do you make those flexible? Well, one approach is to make silicon thinner, and that's certainly the approach that's been taken by companies like American Semiconductor, who have been able to thin down silicon and make it incredibly flexible down to just a few microns in thickness. You can look at other types of materials that could be, for example, higher performance and printable, such as carbon nanotubes, or you can look at things that are potentially cheaper in terms of the materials and or the processes used to deposit those. So that could include organic polymer semiconductors or metal oxide semiconductors, which is the route that we've taken at PragmatIC. So we really see a world at PragmatIC where our technology is able to touch everyone, everywhere, every day. And this is culminated in the Internet of Everything. So it's really a progression of the way that integrated circuits have evolved from the highly complex, highly sophisticated integrated circuits that power our laptops and other devices that have billions of transistors, through to the tablets and smartphones and wearable devices that rely on the low power designs that companies like ARM have pioneered, and these are now in the billions. And this is the next step, really, is allowing every item, any object, to have a unique digital identity. And that could be everything from bottles of wine, through to toothpaste, through to shampoo, through to various cartons, boxes, and so forth. And with that unique ID, you can start to associate data and do useful things for consumers, businesses, and industry alike. And this is the vision of PragmatIC, is to enable this Internet of Everything. So what we've developed at PragmatIC are flexible integrated circuits, or FlexICs, and a manufacturing process to fabricate these in high volumes. So our circuits in many applications are sub-cent, so they're incredibly low cost, and they have a thickness of a few tens of microns, and can be even thinner than that. So they're thinner than a human hair. They're very flexible and conformable, and because they're not relying on crystalline semiconductor materials, they're also durable and shock resistant. So they don't need to be protected by special packaging in order to stop the ICs from being damaged. And also relative to other types of manufacturing, they're environmentally friendly in terms of the types of processes, materials that we use to manufacture those. So this combination of factors brings with it the potential to connect everything. So we really have three different product categories at this point. We have our own Connectic products. So these are RFID products, very low cost RFID, which I'll talk about in more detail shortly. Again, very, very thin, much thinner than the silicon equivalents, and they're flexible, robust, and durable. We've also established a design service that we call FlexIC Foundry, and this uses industry standard tool flows, or EDA, electronic design automation tools, to allow partners to design in our technology. And some of the benefits here, which I'll expand on later in the talk, are that we allow rapid design cycles and very low tape-out costs. And we can work one-to-one with partners, or we can work through things like multi-project wafers or multi-project tape-outs to allow multiple partner designs on a single tape-out. And the final area is FlexLogIC. That's our fab offering. And this is a fully automated manufacturing line that allows companies to get into the business of manufacturing ICs, specifically FlexICs. And each of these lines has a capacity in the billions of units per annum. And relative to the cost of investing in this type of technology in the conventional semiconductor market, very low cost capital investment and a much lower environmental impact. And I'm going to touch across all three of these areas during the talk. So starting first of all with Connectic. So this is our RFID family of products. And really some of the advantages of adding these unique identities, these digital identities to individual items, is that you can start to associate data from the entire product life cycle with the objects, all the way from start of life. So for example, information about manufacturing and source of materials and so forth can be associated with that ID. And this could be important, for example, if there's a product recall or a safety concern, but also to help with audit and compliance through the supply chain, particularly if you think about things like cold chain. You can start to associate information around temperature, humidity, and other environmental factors. So for example, vaccines may be very temperature sensitive, and you'd like to understand whether an individual vaccine syringe has been subject to a breach of a temperature range, which might make it potentially unsafe. And the same could be said for dairy products, even flowers that are being imported from places like Africa. Within the store, there are a number of benefits. One is that RFID brings the potential to massively reduce food waste. So one way you can do this is you can ensure that you sell products within their expiry or sell-by dates. And simply by focusing on this and the efficiencies of a automated digital service to do this, it's estimated that you could reduce food wasted by as much as 20%. And that's a huge saving, not just in terms of the cost of the wasted food, but also the carbon footprint associated with the food production and the transportation costs as well. And then within the home, there are various business to consumer engagements. So offering promotion on reordering, automating reordering, and allowing you potentially in the future to connect to things like Alexa or Google Home Hub. And we also increasingly see the importance of sustainability and the circular economy. So providing information that's specific to the individual pack can allow consumers to understand more about how to responsibly dispose of their waste, how they could recycle more efficiently. And you can start to connect this with other incentive schemes, such as smart bins or deposit return schemes, such as have been successfully rolled out in Germany, where the so-called reverse vending machines allow you to deposit plastic bottles, and in return you receive a fund or essentially a token which you can exchange against repurchase. So essentially, the ability to have an individual ID brings many benefits and a richness of data which can then be put to use to reduce inefficiencies across various parts of the product life cycle. In terms of the RFID tags themselves, so these are essentially, a tag is the combination of the antenna with the integrated circuit or chip. So in the case of a silicon tag, this is a very, very small silicon IC. It's small to minimize the cost, but the overall inlay or tag comprises an antenna. So in the case of a high frequency antenna, it's typically aluminium. And you need to create this bridge to connect the inside and outside of the antenna and complete the circuit. Benefits of using FlexICs is the combination of the low-cost chip and the footprint that we can use whilst retaining that low cost allows us to simplify the tag assembly process. So we can eliminate essentially this additional strap or bridge, and we can use our FlexIC as the bridge. And the combination of this simplified assembly and the lower cost chip allows us to get savings up to 80% of the total tag, which becomes very important as we grow volumes. And we've been able to show that we can create tags or inlays on various substrates, including different types of plastic and paper substrates. So I'm just going to show a short video now. So here we show an example tag that's been produced, and within the packages, we have added these tags, and these are being read by an NFC-enabled smartphone, which then directs the smartphone browser to a unique website, a URL that's specific to the individual item. So this shows that we can create in thin film NFC-enabled tags, very low cost, that are specific to the individual item. And just to give you some examples of the kinds of applications that we can support in RFID. So we're working with global partners across the RFID ecosystems. It's companies like Avery Dennison, which is the #1 company in RFID, SmartTrack, who are one of the leading companies in NFC. So this is the technology that's embedded within smartphones for things like Apple Pay. And earlier this year, Avery Dennison actually acquired SmartTrack. Baoshen, based in China, Smooth and Sharp in Taiwan, and Talking Things based in the Czech Republic. These are some of the publicly available relationships. We're working with many other companies across the supply chain. And it's really the combination of the low price point and flexibility that makes our solution very suitable for these incredibly high volumes. And they're across a range of applications, from beverages, so wines and spirits, pharmaceuticals, so companies like Schreiner, healthcare, waste and logistics, and many, many more applications. And just before I go into a little bit more detail on those applications, one of the most important relationships across the RFID ecosystem is with Mobar. Mobar is the leading company across the world for technology solutions for flip chip assembly of RFID and smart label production. So they have developed systems like the TAL 15000, which is the industry standard for flip chip assembly of RFIDs. They have a very large market share and a installed base in the many hundreds of machines. So these systems allow you to assemble up to 13,000 inlays per hour. And we've proven an assembly process with Mobar that essentially uses the system that's already deployed in the field, and it allows you to assemble FlexICs to make RFID inlays. We're also in the process of working with Mobar to demonstrate this on their DDA, or direct die attach platform, which is an even higher throughput system, more than 40,000 inlays per hour. And there'll be more news on that as and when we develop that through this year. So I'm just showing here another video, and this is a wafer frame. This is a standard format for RFID flip chip assembly. It's a flexible format onto which we have laminated our flexible wafer. The die have been singulated using laser dicing, and we are picking at more than 10,000 picks per hour using the TAL 15000 platform. And on the next slide, we're then doing the next step, which is the placement step. And again, it's using the existing platform without modifications to place at, again, more than 10,000 parts per hour. And similarly, we've demonstrated this process all the way through to the final bonding process. So just to give you some examples now of application areas. So the first one is in waste management, and we've had a project here funded in part by the UK's DEFRA, or Department for Environment, Food and Rural Affairs. And this allowed us to look at where we could deploy our technology within the waste management industry. So it's allowed us to work with a company, Topolytics, who specialize in software for mapping their digital waste tracking platform, WasteMap. And together we've been able to show that you can track movements of waste, and you can generate a richness of data that gives you insights into when and where waste is moving. And this is important because within this sort of industry, there is a lot of audit and compliance requirements, and this can allow you to automate and digitalize that those systems. It's also important for regulators, as it gives them more insights into the types of waste and the movements of waste, and allows them to better target regulation and equally importantly, incentives for businesses. Following on from that, we developed a partnership with the Tyre Recovery Association. So this is a UK trade industry body for tyre recovery, tyre reuse at the end of life. So within the UK, there are 40 million used tyres that enter into the waste stream each year. And one of the problems is that waste tyres are actually a problem waste. They're often illegally dumped onto both public and private land, and that comes with a high cost of cleanup that's either borne by the public purse or the private individual to do that. And that's on public land alone. I think that's more than 15,000 instances a year of what's called fly tipping that involves tyres. So again, just following on from the Topolytics project, this allows a digital process to help with compliance, to understand how waste tyres are dealt with after they've been collected, to ensure that they are disposed of responsibly, where disposable is the end of life, or to track where they go into reuse or reprocessing. Within the healthcare sector, we're working with the National Health Service within the UK, specifically the Gateshead Pathology Laboratory. So across the UK, there are more than 1 billion tests per annum of various different types, whether that's blood or other body samples for a wide range of different potential diseases. And the testing itself is incredibly automated, but the system to manage that from typically the doctor or GP surgery through to the testing laboratory is a manual process. So that's based on paper records. And so there are large amounts of inefficiencies in the supply chain. We've been working with QHS, or Quality Hospital Solutions, to implement a fully digital solution to eliminate these paper trails and to automate the entire end-to-end process, including reporting back of results and minimizing the need for additional GP visits, minimizing the risk of lost samples, and allowing the laboratories to work at a much higher efficiency and utilization of their equipment. And the business case that we've put together with the NHS and QHS demonstrates that just in the UK, this could reduce operational costs by up to £400 million. And we can see that this would also benefit other developed healthcare systems around the world. Looking even bigger in terms of volume, the Ministry of Economy, Trade and Industry in Japan, or METI, has a project with a number of convenience stores in Japan, and they are targeting a problem of aging population and an inability to have sufficient employees to actually man stores for certainly as this goes to 24/7. And they would like to move to automated checkout, and their ambition is to have 100 billion tags, which is the annual requirement, by 2025. So this is similar to the type of deployment that companies like Decathlon have done within their stores, but rolling this out across all items, irrespective of the value. And this really requires driving down to a 1 cent tag, but just for those 5 stores alone, that's equivalent to a $1 billion annual opportunity. And then finally, if we just take one sector, there's even bigger sort of numbers in terms of what can potentially be connected here. So if we look at beverages, something like wines and spirits, so a company like Pernod Ricard, that's about a 3 billion bottle per year industry. We step that up to beer, so we clearly drink more beer. So somebody like an Anheuser-Busch, that industry is 60 billion litres a year. And as we move into soft drinks with Coke and PepsiCo and so forth, we have more than 600 billion servings. And then bringing all of those things together, but excluding water, we're into tens of trillions of servings a year. Now, we're clearly not going to connect all of those within the next few years, but it just gives you an idea of the potential to get into hundreds of billions and trillions of items as we can bring the cost down of the tax. So just moving on now from RFID. So one of the things we clearly looked at when we developed PragmatIC as a business was how are we going to make flexible ICs? So there's been lots of excellent work around printing of integrated circuits, perhaps with organic materials like P3HT or even evaporated pentazine. And there's been a lot of work in the area of printing and roll-to-roll printing, potentially as a large area approach to producing flexible ICs. The approach we took at PragmatIC was really to look at what was available within the conventional semiconductor manufacturing environment. So what we developed is FlexLogIC. So this is really a balance of conventional and proprietary technologies. So we use a lot of well-known semiconductor fabrication processes, off-the-shelf equipment. So we use processes like PVD or ALD to do deposition of thin films. We use photolithography. We use plasma etching and wet etching. And we've brought this together within a compact, so this is a 15-meter by 15-meter system within its own clean room. And it's linked with a proprietary robotic automation and software control system. And what this delivers is a very high throughput, low latency process flow. So we can achieve end-to-end cycle times of a day. And that's delivering more than 10 layers of very well-controlled materials. And as a result of that, we get integrated circuits that are very thin, flexible, and low cost. So each FlexLogIC line has a capacity of more than 1 billion circuits a year. And compared to an equivalent fab in the mainstream industry, we're much lower cost in terms of capex, so more than 100 times lower, very low footprint. So rather than the kind of small cities that you would see for a mega fab that requires its own power station, we're more than 100 times smaller. And rather than talking about many months in terms of cycle times, we're talking about hours to produce our circuits. So our typical process flow is actually quite analogous to other semiconductor flows. So we prepare a substrate, and this is a polymer film that's deposited onto a carrier that can be either glass or silicon. And then we go through a series of deposition and patterning steps. So multiple layers go through that step. And we do thin film deposition and then pattern transfer to create step by step, layer by layer, our 3D integrated circuit. Once that process is finished, we can then program data. So we have a laser programming step that can add the unique ID in the case of RFID. And then we have functional test, and we prepare for assembly. So again, in the case of something like RFID, this would use a wafer frame format that is intentionally designed to seamlessly fit with the existing supply chain. It's a very high efficiency scheduling that allows us to optimize throughput. We get multiple layers of finely tuned functional materials, and we can configure this FlexLogIC system for multiple different products and process flows without impacting the efficiency of the overall system. Compared to silicon ICs, the model is intentionally designed to support a number of manufacturing sites that can be distributed globally. So that can be across multiple applications, multiple geographies, and different industry supply chains. So our vision is to allow more people to enter electronics manufacturing, since they don't require highly specialized expertise, and because the capital cost is not prohibitive. And we really see this as a democratization of the manufacturing. The first fabs are in the UK, but we expect the next fabs to be located overseas, and we can see also the opportunity to connect these fabs into essentially a smart grid, allowing us to have remote process and machine control, and to ensure that we get consistency of production across the sites, to have continuous learning and monitoring for quality assurance, and to allow us to really to aggregate these learnings for optimization. So again, if we go back to something like RFID, this allows us to actually compress the supply chains and to remove some of these multiple margin stacks or parasitic margins that come in when you're moving goods across multiple locations and geographies across the world. And we see this really as being essential to strip out unnecessary costs and to grow into the billions and trillions of units over the coming years. So just going to show a short video now of our FlexLogIC line. So you can see here one of our glass carriers with our polymer film coated on it. We're using standard processes like spin coating of photoresist to get high precision, as I mentioned, PVD, buttering, and ALD. And then this would go into a photolithography step. We have a transport system that moves the wafers between different process modules, and all of that's fully software controlled, no human intervention required for any of that. We do etching processes. It's hard to show the plasma-based etching, but here you can see processes like wet etching and stripping and cleaning processes. Again, all robotically controlled. And then we also have inline inspection for checking and quality purposes. And then this is the first point of human intervention. When the finished wafers are taken out of the line and they go through to testing, inspection, laser programming, and singulation, and then preparation for assembly. We remove from the carrier, which is recycled and reused, and then they're ready for automated assembly. So again, moving on from FlexLogIC, I'd like to talk about our FlexIC Foundry service now. So this is a design service that we've developed over the last several years, and it really builds off the fundamental building blocks that we've got. So we have various devices, thin film transistors, diodes, resistors, capacitors. At the moment, this is unipolar, so it's an N-type metal oxide semiconductor, and we get models associated with all those devices, design rules, and a cell library of gates, including things like flip-flops that can operate in the tens of megahertz speed. We work with partners who have a product specification, and one of the key advantages here is that we can do multiple iterations to produce an optimized FlexIC. Because of the cycle time and the design cost being so low, we can work with them to do iterations through schematic design, layouts and fabrication, test and verification, and then repeat around this loop multiple times. Delivering to them are flexible ICs, either mounted onto glass or in another format, depending on their requirements. And this allows you to move from concept to product in a matter of days or weeks rather than months or years. So I think everybody has heard of Moore's law. It's actually originally an observation by Gordon Moore more than 40 years ago, that the number of transistors per area was doubling every few years, but it's really driven the mainstream silicon electronics industry for many decades. And is there a Moore's law for FlexICs? Well, one of the interesting things about silicon ICs is there's actually a a minimum size of silicon below which it doesn't make sense to reduce the complexity, because essentially the size of the silicon die becomes limiting. You can't have a cost-efficient silicon die with only 100 or 10 gates. So here we show a comparison of the cost of the IC. So for two different generations of silicon technologies, this excludes the capital costs. This is a fully depreciated fab in the case of silicon, compared to the FlexIC Foundry costs, which includes the capital costs. So you can see for certain complexity of products, the FlexIC is more than 10 times cheaper. And actually, if you remove the capital costs, it's an even bigger gap. We don't compete in the very high complexity, in the hundreds of thousands or and beyond in terms of the performance of the chips, and we're not looking essentially to compete with silicon. But the sweet spot is in the hundreds, thousands, and ultimately tens of thousands of gates that's achievable within a small footprint, cost effectively, and not competing with silicon, but in opening up a new range of applications. And we can see over time that we can move from the current 0.8 micron technology, our capabilities already down to 0.3, but there isn't a big driver to really squeeze in the same way that silicon has the channel length and the footprint in the same way. But we will be pushing complexity up and the overall cost down as we improve on our process and manufacturing solution into this area here as described. Another consideration that's often overlooked is the design cost. So again, although we're not competing with it, it's a useful reference point to look at silicon foundry models. So as new technology nodes are developed in silicon, the design costs are increasing exponentially, from millions to tens of millions, and in some cases even hundreds of millions. And for bleeding edge technology, it can be hundreds of man years that can go into designs. So there's really a very high design cost, and there's a requirement that designs are right first time because of that. With the FlexIC Foundry, we really just focus on good enough performance. We have a very low design cost, and coupled with the fast production cycle time, we can afford to do multiple design iterations. We can afford not to have to get things absolutely right first time. I think this is a key difference in terms of our approach and the kind of traditional approach that has been the way that the silicon industry has developed. So just to look back now, more than 40 years, to one of the first commercial microprocessors developed by Intel, the 8080. This was an 8-bit microprocessor on a 6-micron enhancement load NMOS technology, running at a pretty modest 2 megahertz clock speed and a fairly power-hungry 12 volts. It's around about 6,000 transistors and 20 square millimeter die size. But interestingly, even despite that, and I suspect despite pretty major yield challenges at the time, they were able to get a return on investment on the R&D within a matter of months. So some of the things that we've been working on are projects with ARM, the University of Manchester, and Unilever, called Plastic Armpits. This is a machine learning circuit for an electronic nose, and it's focused on malodor or body odor, but it's also analogous to other types of sensing, which I'll touch on later. So what's been developed here is something that you can highly customize in the hardware to the specific application. It gives you parallelization of the solution. So it's fault tolerant and very low cost. We've also been working with ARM on microprocessor using their Cortex-M0 platform. This is a system on chip, or as we're calling it, system on flex chip platform. And we've done multiple iterations of this design, and we've been able to work with ARM to introduce tighter design rules, so not just scaling channel length, but other features, including interconnect and the cells themselves, to get a shrinkage of more than 90%. So this is now within a few square centimeters, and we expect to make further big wins in terms of footprint over the coming year. So we have a number of Foundry partners already that have been announced, and many others that haven't been announced, and we're working with them to help to create innovations. So these are R&D organizations like IMEC, design specialists like ARM and Cambridge Consultants and CIRMA, and companies like Talking Things who want to develop their own commercial projects. So why are they working with PragmatIC? Really, it's because we can offer very fast development cycles. We have this design, test, iterate and repeat capability because it's lower cost than silicon. And importantly, we also have the route to scale this up to hundreds of millions of ICs at low cost. So we're not just offering a handful of test wafers, we're also offering a route to scale up. And we're very happy to talk to other people around the FlexIC Foundry model. So in terms of the circuits, so there's a paper published by the Technical University of Dresden, working, designing in our technology, designing transimpedance amplifiers, and they've demonstrated pretty good high gain bandwidth performance that would be suitable for RFID circuits within a compact footprint of just 0.3 square millimeters. I touched on the next one earlier. So this is the project with ARM at the University of Manchester. And actually, this was published last month and featured on the front cover of Nature Electronics. This was the hardwired machine learning engine with a submicron metal oxide TFT technology on a flexible substrate. So the machine learning engine was created using a malodor training set from Unilever and sensor data from the University of Manchester's sensor technology, designed by ARM and PragmatIC and implemented in the TFT technology. And as I said earlier, although this is a good example of a malodor application, we see this as being extensible to other areas that could include, for example, food spoilage. We're very grateful here for the support from UKIR and Innovate UK, who have helped to fund some of the development here. Just to give you an idea, compared to the Intel 8080 design shown earlier, this has more than 2,000 TFTs, more than 1,000 resistors, and that's within a just over 5.5 square millimeter footprint. If you'd like to know more about this, Emryoza from ARM has given a paper, which is a recorded talk on this in more detail, and you can find that on the Flex website, and it's paper ID 2096. And of course, there's been quite a lot of other designs that have been implemented in metal oxide semiconductors and film TFTs. So a few examples here. So IMEC and TNO and TUE and Eindhoven have implemented a heart rate measurement interface using IGZO on Flex. Shanghai University have created a multi-electrode array for EMG, so that's looking at neuromuscular activity, again using IGZO TFTs on polyimide. And then there's been various activities towards displays and flexible displays, so sharp as an example, I've done a paper combining oxide TFTs with P-type low temperature polysilicon to get CMOS capability, integrating driver circuitry on a flexible display. And then finally, again, IMEC and TNL, but this time with Evonik, did a nice hybrid CMOS implementation solution processed, combining organic P-type and metal oxide N-type to demonstrate a low power RFID tag. So in terms of the FlexIC Foundry roadmap, looking ahead, we're looking at analog functionality. So we've developed a range of different sensor interfaces, analog to digital and digital to analog, for example. We'll be increasing the circuit complexity, so the device at gate counts, and looking at things like the system on FlexIC I touched on earlier, and also with a view to higher performance, so into the gigahertz frequency and reducing power. So I'm just going to finish with a couple of examples of things that we've worked on. So one is a Schottky diode technology, and we see this as being essential for high performance. So we've created a novel Schottky diode. You can see the structure here. So we have a flexible substrate with a barrier. We have an anode dielectric, and then the semiconductor with the cathode. So it's a combined vertical and lateral structure. We've implemented this without using expensive noble or platinum group metal materials, which is important from a commercial perspective to make it viable. We've been able to implement this on our standard FlexLogIC line alongside our existing TFT process, and we get good consistency of the characteristics across the wafer that is important for scale up. So again, there's a top-down optical image here showing the anode, semiconductor, and cathode. A little bit more on the Schottky diodes. So we find that the efficiency of the energy harvesters is much better than using TFT equivalents. We get good rectification ratio, 5 orders of magnitude, with a very low forward drop. We can tune the properties by varying the lateral separation of the diode. So this allows us, for example, to minimize the off-state currents. We can increase the reverse breakdown voltage. And we've also been able to demonstrate performance in the gigahertz range. And actually, this is the limit of performance of our test equipment. I know there have been other publications that are higher than this, but I'll just remind you that this doesn't use gold or platinum or other materials, and it's something that can be scaled up commercially. And we've also, with this, seen a significant reduction in the footprint of the circuit, which is important both from a yield and a cost perspective. We've also worked on thin film memory on Flex, and this has also been partially funded by UKRI, again, Innovate UK, working with groups at the University of Exeter and University of Southampton. We've developed a non-volatile memory on Flex. We've got large resistivity range between the different states, rapid switching, and long retention times. It's a type of materials that have already been used widely in things like recordable CD and DVD technologies. And although we haven't implemented this yet, it is also compatible with something that's rewritable. This is on our pilot process. Again, no expensive metals such as gold or platinum have been used, and we can integrate this with a TFT process. So you can see here in the read cycle, before writing, we have a 0 state, and then after writing, that switches to 1. So what we see at Pragmatic is that we want to work with innovators to build solutions that are extraordinary, that can improve everyday life, that have societal benefits. We want to enable future applications that haven't yet been imagined to really help to drive this move that we've seen in the industry, from components to integrated systems into higher value applications. We have our ultra-thin FlexICs. They're a fraction of the cost of silicon, and we developed Connectic RFID products that we believe will enable the Internet of Everything. We've also developed a foundry model to support rapid iteration of new designs and to democratize this and open it out to the design community. And we have FlexLogIC that revolutionizes the semiconductor manufacturing. We have a very bold vision to get our technology into more than 1 trillion smart items over the next decade. And my challenge is, what will you create? Thank you.
Thanks. Thank you, Richard. That was an excellent presentation and real insight into the flexible integrated circuit world. There are quite a number of questions that were posted on the chat, webinar chat. So I'll just go through. I'll read a question at a time, and you can then take your time and answer them. Yeah. So the first question is says metal oxide semiconductor is typically known for its instability at ambient condition. Would you comment on how robust does the current encapsulation technology designed to overcome this issue?
Well, I guess there's a few ways to answer that question. One is it's important, I think, to characterize the stability of your technology, and then you can you identify applications that are suitable. So we're not looking at 5 or 10 year lifetime applications. Many of the things we look at are very small number of uses. Our experience with metal oxides is actually they're rather robust. So from certainly from an ambient storage condition, we have many years of lifetime there. We don't use particularly special barriers in that the tags themselves are passing temperature, humidity, thermal cycling processes. We use modest temperature processing, up to 200 degrees Celsius would be typical within our manufacturing. So I think they're not equivalent to a mainstream semiconductor component, but actually we find that they are, I guess, rather robust in terms of their stability. Right.
Okay. The next question is, have you developed or considered what to do in the future, the RFID NFC tags with any sensing capability, for instance, temperature? And can this be an additional feature to only identification or tracking?
Yes, and yes, I think are the answers to that. So, they're not yet available commercially, but absolutely temperature, humidity sensing is very much on our roadmap and something that we have already worked on.
Okay, thank you. Next question, is your service to NHS QHS only the HW or the whole architecture involving DAQ, data processing and delivery of results?
Okay, so we don't do software solutions, so we don't get involved in the data side of things. We offer the hardware solution.
Okay. What's your opinion and applications of your solution for wearable market sector? How long do you think it will be before printed electronics will be commercially available or for consumer 3D printed solutions?
Yeah, it depends what you mean by wearable. So I think we are some years away from, I think, quite complex systems combining many components for wearables. I think there are some interesting opportunities for single use, particularly within the healthcare sector that we've already heard about some of these through the conference, but I think realistically they're all, I think, several years away from being commercial reality. But I don't see a replacement for, say, a Fitbit or something as complex as that. But there are opportunities for hybridization there to simplify some of the things that silicon does inefficiently and replace those with a flexible solution that could make the overall wearable more comfortable and flexible.
Mm-hmm. Okay. So next question is, what plastic substrates are available? There are about 2 or 3 questions here. So that's the first question. Is it also possible to use hyper-elastic polymer silicones as substrates? Maybe attached to a carrier wafer for subsequent release? And last of all, what's the critical dimension of the flexible IC? Sorry, you want me to go question by question and you answer?
That's fine. No, so I think I mentioned that the current critical dimension is 0.8 microns that we use, but we have the capability of going down to 0.3, but we haven't made that step yet. In terms of other substrates, I think in concept it's possible. It's about then thinking about different coefficients of thermal expansion. What is the end use case for that? Because you can introduce stress into the substrate, which may be detrimental, it may not. So it would need to be, I guess, treated holistically as part of the process. But potentially other substrates are possible, and I think people have certainly demonstrated on a range of different types of substrates. But we've used polyesters and polyimides predominantly.
Okay. Right. Next question. Can you please name the software or simulation platform used at PragmatIC for Flex chips?
So this is EDA Toolflow. I'm not going to name the vendor, only to say that we work with top tier EDA solution products. So they will be familiar to anybody who is an IC designer. Okay.
Right. Now, next question. Are you using near sensor processing before loading the process data into ML modules?
So this is kind of a question around signal processing. I would encourage I think SM to listen to Emre's talk and to read the Nature Electronics paper. I think that will give a much better answer than I would at this point.
Right. The next question says, Richard, very nice presentation, nice overview of capabilities. Thank you. What's pragmatic vision on complementary technologies, LTPO or metal oxide P-types? As we know from silicon CMOS, this has really led to a major breakthrough, and I would expect similarly for FlexLogIC.
I'd agree, and I think it's something of interest for you also, Arukia.
I don't believe in metal oxide for P-type, though I can tell you that.
We have several, we've been working on P-type metal oxides with various partners for a number of years. Yeah. They are not yet there, but I think we are close to something that is useful, if not the ideal P-type metal oxide.
I see. And how stable are they? Thermodynamic stability? Can you comment on that?
Yes, I think that if you're looking at it from having the full CMOS benefits, I think that is one of the challenges, the stability.
All right. Last question. You'll be spared after this. Great presentation. Thank you very much. Could you comment on the yield of the large chips that you talked about? And also, what's the roadmap for the memory and diodes that you talked about?
So, yeah, I mean, obviously, as you go to larger die, the same yield challenges are there as you would have for any wafer-based process. They're not yet commercially viable for those large chips, unlike the RFID products where we can get very high yields. So I think there's a combination of reducing the footprint there and improving the process to get that commercially viable.
Okay.
I think the roadmap, we are, I think, as I said, for the Schottky devices, that's already being implemented into a manufacturing process, and we expect to release that as part of an updated PDK. The memory will take a little bit longer. It's available, but it's not something which is yet receiving sufficient commercial pull, I think.
Okay, good. I think I'll bring this plenary session to a conclusion. Thank you very much. It was excellent, and a good list of questions that were put forward. Thanks again very much, Richard.